graph, it opens up. If I have a negative leading coefficient, it opens down. Well, the good thing is we can apply that across multiple different polynomials. In fact, we can come up with a nice little set of easy ways to tell what happens at the ends of any polynomial equation. So first of all, graphs of polynomial equations, they're going to be continuous. They're always going to be continuous. That means there's basically no holes or breaks. They're also going to be smooth. That means that they're only going to have round curves. They're going to be nice round curves, not jagged, sharp turns like an absolute value graph. That's a jagged turn. So it's going to be smooth. It's going to have only round turns. I.e., when you're talking about a quadratic, it's just a nice round shape. There's going to be no jagged turns or no quick turns. It's not going to go back on itself. It's just going to be a round, smooth curve no matter where it changes directions. All right, the next thing we're going to get to is something called the lead coefficient test. We already did this with quadratics. Like I was saying, if we had a positive lead coefficient, it went up. It made a U shape. If you had a negative, it went down. It had an upside down U shape. Well, let's start off with if f is an odd degree function. An odd degree function is going to be something like x to the first, x cubed, x to the fifth, x to the seventh, x to the ninth, x to the 11th. Anything that has a lead power or highest power being odd. The first thing we're talking about is if a sub n is bigger than 0. That means your lead coefficient is positive. That is your lead coefficient. Then the graph falls to the left and rises to the right. So it's going to look something like this. We don't actually know what happens in between, but we do know it's going to go up this direction and it's going to go down this direction. In other words, let's just put it a different way. Y goes to negative infinity as x goes to negative infinity. As x values get smaller and smaller, so do your y values. It goes up would be referred to as y goes to infinity as x goes to infinity. So anytime we have an odd power, your biggest power is odd. If your lead coefficient is positive, it's always going to go down in the left direction, up in the right direction. Well, if your lead coefficient is negative, they're just going to switch directions. They're just going to switch directions, where if you're going left, it's going to go up. When you go right, it's going to go down. So that same graph that we had up there would look something like that. That would be written as y goes to infinity, as x goes to negative infinity. I should probably have an as in between there. And then we write down here, well, y would go to negative infinity as x goes to infinity. So these are for all odd polynomials. You just have to look at the lead coefficient. You just have to look at the lead coefficient. What can help you remember which direction things go is just graph y equals x. That's a very basic odd function. And when it's positive, it goes from down left up high. And if it works for y equals x, then it's going to work for any odd power polynomial. All right, the last one is if f is even. We already did this one. We already did this one. We said, well, if our lead coefficient is positive, it's going to go up. It's going to make a U shape. So that means that's going to apply for any even degree. So we're talking about x squared, x to the fourth, x to the sixth, x to the eighth, so on, so on, and so on, and so on. So if your lead coefficient is positive, it's going to go up in both directions. We don't know what happens in between. Maybe it does something like this. That's probably a terrible one. But it could do anything in here, but we do know that it goes up on either ends. If your lead coefficient is negative, it goes down in both ends. We don't really know what happens in between, but we know what happens at the end. We already did that. It works for x squared, so it's going to work for x to the fourth. It's going to work for x to the sixth. It's going to work x to the eighth. The only thing we don't know is what happens in between. So let's go ahead and draw the end behavior of each of our polynomials. So for each of these polynomials, all we have to do is determine whether it's odd or even, and then find our lead coefficient. Either it's positive or it's negative. It's the only two things you look for if you're looking for end behavior of a graph. So our first one, our biggest power is x cubed. That cubed is definitely odd. And then we look at that 2. Well, 2 is positive. Odd means it goes in opposite directions. If it's positive, it's going to go down and then up. Down and then up. Our next one is 6x to the fourth minus 5x squared minus 1. Its biggest power is that 4. Well, 4 is even, and 6 is positive. If it's even, it either both goes up or both goes down. Since it's positive, they're both going to go up. On the test, at the very least, you should know odds go in different directions and evens go in the same direction. Then you just at least you have a 50-50 shot of doing it. So odd goes in both directions, evens go up or both down. Remember, just think about the most basic odd and even functions. That is y equals x. X is a straight line that both ends go in opposite directions. X squared, we should all know, is a U-shaped. So apply that to the rest of them, and it can help you remember what's going on. All right. Our next one, we have to look at the biggest power, not just the first one that's written. 5x is the first one that is written, but the biggest power is 4, which is even. And there is a negative number in front of it. Even says they both go in the same direction. Negative says they're both going down. Our final one is negative 12x cubed plus 9. Well, that's odd. And that negative 12 is negative. Once again, if you're on the test, you know they both go different directions. At the very least, you should be able to have a 50-50 shot at it. Well, if it's negative, as x goes to negative infinity, it will go up. In other words, it's going to go up on your left-hand side. And it's going to go down on your right-hand side. In other words, where x goes to infinity, our x or our y will go to negative infinity. Once again, just picture y equals x looks like this. Y equals negative x goes in this direction. That can help you remember on a test. Break it down to the basic ones. All right, let's continue on. Continuing on, we're going to go to zeros of polynomial functions. Now, for a polynomial of n degrees, we said the function has at most n real zeros. So we look at the biggest power, and it has at most that many real zeros because your n power tells you how many zeros you have, whether that be real or imaginary. So you can't have more zeros than your highest power. So if you have an x to the fourth, equation, at most you have 4 real zeros. Because we said it has 4 real zeros, we don't know if they're all real. They could be all imaginary, but it has at most 4 real zeros. Well, the graph has at most n minus 1 turning points. These are your relative mins and your maximums. In other words, a turning point is going to be this. So say we have a graph like this. This would be a turning point. This would be a turning point. So it would have 2 turning points. Note, it could have 3 zeros too. So when we look at the power of a function, say we have an x to the fourth, it has at most 4 real zeros, and it has at most 3 turning points. That can help you when you're coming up with rough sketches of these. No, you zoom out, I say. All right, let's talk about repeated zeros. So we talked about this when we were talking about finding all of our zeros. We said when we had something like x minus 3 quantity to the third power, we said we'd have x equals 3 is a 0, but it has a multiplicity of 3. So we're really talking about multiplicity here. So anytime we factor an equation and it comes out to x minus a to the quantity k, where k is bigger than 1, it yields what's called a repeated zero or a multiplicity zero, where x equals a and has a multiplicity of some numbers. Well, if that k, if you have a multiplicity of an odd number, so if you have a multiplicity of 3, then the graph crosses the x-axis at x equals a. It actually crosses through it. So the example I came up with was, if I have y equals x minus 3 to the third. For our 0, we have x equals 3, but with a multiplicity of 3. That is odd. That is odd. If you have a multiplicity that is odd, it is going to cross through that point. So without going into detail of what this graph looks like, I know for a fact that at 3, it's going to cross at 3. So it crosses at 3. If your multiplicity is even, it will not cross at that point. It's going to actually bounce off it. So if k is even, the graph is tangent, or it just touches and then changes direction. It won't actually go through at that point. So my example for this one would be y equals x minus 2 squared. Our 0 is at x equals 2, and it has a multiplicity of 2, which is even. Even tells you that it will not go through that point. It's going to bounce right off it and go back to where it came from. So in this example, 2 is our 0, 1, 2 is our 0. But it's not going to go through. It's going to touch it, and it's going to bounce right off it. So odd multiplicity, it goes right through. Even multiplicity, it bounces right off. Now, if we combine this information with our n behavior, you can actually get a really good rough sketch of any polynomial. We already could do a really nice sketch of a quadratic because we could locate our zeros where they are. We know if it's going up or down, so we can actually do a really nice graph of our quadratic and actually have a good enough quadratic graph that we can determine where it's bigger than or equal to 0. Well, that's exactly what we're going to do for powers that are greater than an x squared. So in our first example, we have x cubed plus 2x squared minus 3x. We're supposed to sketch a quick graph. It's actually a pretty accurate graph. Honestly, we can gauge a lot of material from it. So it's an actually very accurate graph. We start off with what's going to happen when I go x goes to negative infinity and x goes to positive infinity. In other words, we're going to talk about our end behavior. And that means we're looking at our leading coefficient test. Leading coefficient test is going to test for our end behavior. So the first thing I'm looking at, what is our biggest power? Our biggest power is 3 in this case. Well, 3 means that the arms kind of go in opposite directions. So even if I'm not sure what I have to do next, you can at least do a 50-50 shot at it. But currently we have, and I'm just going to look at my x cubed. That is our lead coefficient test. So I'm going to take that x cubed and look at the power it is. Well, it's odd. And the coefficient in front of it is positive. If it's odd and positive, our end behavior is going to start low and end high. Now to figure out what happens inside here, we're going to locate our zeros. We're going to go ahead and locate our zeros. In order to locate our zeros, we're going to go ahead and factor. We're going to go ahead and factor. We have other methods of finding zeros. Our last whole section was, how do I find zeros of things that were bigger than a quadratic? So in this case, we have x cubed plus 2x squared minus 3x. So the first thing I'm going to do is I'll factor out an x. So we'll rewrite this as factoring out an x, because there's an x in each one of those. That'll be x squared plus 2x minus 3. We should be able to factor this further. We'll have x, and we'll have x. We have to make negative 3, so we must have a 3 and a 1. That 2 is positive, so we'll have a positive 3 and a negative 1. Ooh, I took up a ton of room on mine. You should have a lot of room in theirs, right? Okay, good. All right, that leaves us with 3 zeros. It leaves us with 3 zeros. We have either x equals 0, x equals negative 3, or x equals 1. But now, more importantly, I have to determine what the multiplicity of each of those are. In other words, we're looking at the powers that are above our entire quantity. Well, if we look here, it's x to the first. It is x plus 3 to the first. It is x minus 1 to the first. So they all have multiplicity of 1. So this is multiplicity of 1. This is multiplicity of 1. This one is multiplicity of 1. So they're all odd. So they all cross. So at x equals 0, our graph is going to cross. At x equals negative 3, our graph is going to cross. At x equals 1, our graph is going to cross. You should draw this down below. I just ran out of room, so I'm going to move it over here. But you guys just put it below this stuff, because you should still have room down there to do the graph. So you guys go down. I'm going to go over. Are we all on board? All right, so our graph of this is, I'm going to plot points at each one of our zeros. We have a point at 0. We have a point at negative 3. 1, 2, 3. That'd be negative 3. We'll put a point there. And we'll have a point at 1. These are all our zeros. All right, we start low. And it says we're going to cross at each one of these. So I'm going to cross through negative 3. The graph is drawn to our next 0, which it has to cross. And it has to cross at the last one and end high. most of the time. In fact, this is the way I checked to make sure everything was done correct. I just start low, it crosses, 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 and then I make sure that it should end high. All right? Because there are times you're going to make a mistake and all of a sudden it's going down. You're like, wait a minute, it should have ended high. And then you figure out which one of those should have bounced versus crossed. All right, but that's it. That's all we're doing in this chapter is we're looking at our lead coefficient to determine what our end behavior is. Find your zeros and determine if they cross or they bounce at those given zeros. Let's do the same thing for this next one. Do we all have this graph down? All right, because I need to erase it. I need that room. I need that room. All right, the first thing we're going to do is we're going to look at our lead coefficient. First of all, our max power is even. Our lead coefficient is positive. So this graph's end behavior should be up and up. It's even, it's positive, up and up. All right, the next thing we need to do is we need to actually factor this guy. Well, what I'm going to kind of look at it as, what I'm going to kind of picture this as is x squared minus 200x plus 10,000. Because we can treat this the exact same way. Because if I just put an x squared and an x squared out here, x squared times x squared gives me my x to the fourth. X squared plus x squared gives me my x squared. So now all I'm doing is I'm looking for a number that multiplies together to give me 10,000. And when I add it together, it gives me negative 200. What would those numbers be? Got an idea? Yeah. 100 and 100. Negative 100. And negative 100. Well, 100 times 100 is 10,000, right? And negative 100 plus negative 100. All right, so we're good. We're good there. Well, let's look what this breaks down into. This breaks down into x minus 10 times x plus 10. You could have also just done x squared minus 100 and found your zeros that way too. This one will also break down to x minus 10, x plus 10. Note there is a multiplicity in there. So if I say x equals 10 is a 0, x equals 10 is a 0 is also here. That's multiplicity of 2. If we look at x equals a negative 10, this is also an x equals a negative 10. That is also a multiplicity of 2. So either you can recognize that x equals 10 happens twice, and x equals negative 10 happens twice, or you can rewrite this further and go, well, this is just x minus 10 squared times x plus 10 squared. Most of the time, I would just stay here. I would say, okay, 10 happens twice. That's multiplicity of 2. Negative 10 happens twice. That's multiplicity of 2. All right, well, let's write our zeros. We have x equals 10 with a multiplicity of 2. And x equals a negative 10 with a multiplicity of 2. So that means its multiplicity is even. Even tells you it's going to bounce off at those points. So a multiplicity of 2, that's even. This is even. Even tells you it's going to bounce. Even equals a bounce. Odd equals is going to cut through. Even equals is going to bounce off. I'm going to kind of have a smaller graph just so I can fit it on that same sheet. Well, it looks like we need to go from negative 10 to 10. So let's just go negative 5, negative 10. We will go 5. We will go 10. All right, we said it's even. It's even, so it should start high and end high. Well, let's see what happens. So at negative 10, it's supposed to bounce. So it's going to bounce off. Then it has to make it back when it hits 10. So it'll bounce off at 10 and go up. Once again, at negative 10 and 10 it bounces. It starts high, it ends high. This is our graph. It's a big old W. All right, questions on that? But those last two problems are really everything that's in this section, or this part of the chapter. We're just coming up with quick sketches. Once again, that is a lead coefficient test. Find your zeros, determine if they bounce or cut through. That is it. Those are your three only steps in this whole section. All right, guys, the rest of the time is yours.